Hello students, we are doing our last section of chapter 4. We are looking at applying proportional reasoning in a different way. Specifically, we are looking at application in terms of scale. Um, you probably, you must have heard about scale if you took any kind of geography. So I was just highlighting this that when we have a scale drawing, it requires some kind of proportional reasoning. And when we're talking about scale, we're talking about representing something in real life and then representing it either in an enlargement as a bigger image than what it is, or as a smaller image than what it is. So that's where if we're representing something that's bigger than the originally set up, it would be an enlargement. If it's smaller than the original, then it would be a reduction. So that's pretty much what we're looking at in terms of scale. If you took geography, you probably would have looked at some maps, and I went and found an example. So here's a map of Canada. Um, I think I can zoom out there. Oh, yeah, there we go. So if you look at it, this is what a map usually looks like. And then on the map, usually there's some kind of a scale. So down here at the bottom, if I click on it, you will notice that there's something that looks like this. So what this one says is that 1 inch on this map is equal to 191 miles in real life, or 1 centimeter on this map is equal to 121 kilometers. So that is the scale that's given to us, and what that really means is that we could take this map and we could take a ruler and then start measuring things. So let's say we could measure from Ottawa to Montreal, and we can see how many centimeters that is, and then we can actually estimate how many kilometers that is in terms of distance. So that's what scale is used for, um, where you've seen it in geography. It is used in a lot of other situations, a lot of manufacturing. Let's say you're making some kind of a car, and before you get into large-scale production, you might want to make a model car so that you can kind of work out the details and sort all of that out. So scale, that's what it is. Um, Usually there is a scale factor that we're dealing with. So depending on what your scale factor is, you're going to know if you're either making something bigger or if you're making something smaller. So when you're using a scale factor, you're going to use some kind of well, not some kind. You're going to use a multiplication. So you're going to be multiplying the actual dimensions with the scale factor. And that, when you multiply with the scale factor, it's either going to make it larger or make it smaller, or maybe even leave it the same. So if we have a scale factor that is equal to just 1, which is also the same as 100%, you will get the exact copy of the original. So same size, same everything. Anything larger than that, so if you're multiplying with a number that's larger than 1 or more than 100%, you will get an enlargement. Similarly, if you're multiplying with something, a number less than 1 or less than 100%, you will get a reduction, a smaller size object. Usually when we're representing this scale ratio, we have the diagram measure compared to actual measure. So diagram to actual measure. Here it's kind of set up in a ratio form, but we can use we will use more of a fraction form. And how we're going to use that in fraction form is that we're going to create proportions, and we're going to calculate things that we're looking for, some unknowns. All right, so that's kind of the general gist of our lesson. There is an example here where I think, yeah, they're comparing the hex hex nut bolt, and there's usually some diagrams. Sometimes if you look at this one, it shouldn't be this big because it seems pretty huge. So this would be an enlargement, and you can look through the example. They go through some calculations and all that stuff in the solutions. We're just going to go straight to our practice questions. Oh, there we go. So the first practice question, we're looking at scale factors. We have two shapes, A and B, and we're going to try and determine what happens between um, the two shapes. Does it one enlarge? Does it reduce? That sort of stuff. So our original is our A, shape A, and then B is going to be our either enlargement, or maybe we'll have one that's the same. It looks like no. So it's either going to be larger or smaller. So we'll look at the first one. We need to find the scale factor, and we're going to write it as it says here. Let me just shift to my pen. It says here we're going to do it as a number and as a percent. So let's set it up as a number first. All right, so I will start first by looking at these shapes. It looks like we have squares. Um, Sometimes they'll be rectangles, whatever shapes. In this case, we have squares. I look at my original A shape, and it says that the original side length, if you want to look at it here, it is 2 squares. So I'm going to put 2, 2. And then the for the second one, it seems like it's increased to 4. So if I want to get a scale factor, what I want to do is I want to reduce this ratio. So I want to reduce it until my measurement for A is equal to 1. So it's kind of like a unit rate that we've been doing in the previous section. Kind of like that, but we're going to adjust it a little bit. So this is where we're kind of doing the equivalent fractions. We're going to reduce both of them by the same amount. In this case, you can see that you can divide both by 2. So that reduces to just 1 to 2. So that means that the second shape, shape B, has increased by a factor of 2. So that means that my scale factor is 2. If I'm looking at percent, I can set up a little proportion. I have the original was 1. The enlarged one is 2. And I know that the original is 100%, which means that if you remember, this is times 100. This is also going to be times 100, which means that this is 200%. So 2 and 200% of the original. All right, next one is a circle. So B is a circle. You can see that A is smaller. It's inside. We're going to look at radius. So radius from here, from the center to the outside of the circle, it seems like it's 1 square, and that is compared to 1, 2, 3 on the radius for B. That gives us right away that our scale factor is 3, which means that B is 3 times larger in terms of radius. And if we look at percentages, that should be 300%. All right, the other one, triangle, we're going to see. You can see that the original is 3, and the second one, B, is just 1 square. So hopefully you can see that it kind of gets smaller. But remember our strategy. We have to reduce the original one so that it's equal to 1. So if we divide both by 3 here, we're going to get where our scale factor is. So if you don't have a calculator, 1 divided by 3 is this, 0.333, and so on. So in this case, we know that our scale factor is 0.333, and in terms of percentages, this will just be 33.3%. I'll round it to that. There we go. So that means that there's the B is obviously smaller, and 33% of the original size. Last one, it looks like it's a square, but we're kind of looking at it as a diamond shape. I'm going to look at it in terms of a diagonal. So I'm going from up here all the way down, and that's going to give me a comparison. So if I count 1, 2, 3, 5, 6, 7, 8, 9, 10. So 10 for the original, and just 2 for B. So again, we have to reduce the original, so it's just 1. which means it's going to be 0.2. So a scale factor of 0.2 and 20%. You might have noticed that I just multiplied this by 100 to get the percentage. So in this one, part D or question D, the second shape is 20% of the original. All right. Second question is related to the first one. It says state whether shape B is an enlargement, which means is it larger or is it a reduction from shape A? So the first one we had go from little square to a big square, so this is an enlargement. Let's put E for enlargement. B, we had a little circle A and big circle B, so it's also an enlargement. For C, we have triangle A is a large triangle, and then triangle B is smaller, so it's going to be a reduction, which I will put R. Maybe I should put like this is E and this is R. And then this diamond shape, also a reduction. It just went from large A to a smaller B. All right. Now we're moving to a similar question, but we were given the original, we're given the scale factor, now we have to reproduce the second shape where the scale factor is applied. So the first one, we have a little triangle here, a scale factor of 3. That means that it's going to be increasing by 3 times. So that means if my side length here is 2, the new one is going to be 2 times 3. I'm just getting a ruler ready. So that means my side length is going to be 6. So I'm going to take a ruler, 2, 4, 6. There we go. And the height is also 6. Oops, 2, 4, 6. I'm just going to move it over. Definitely use a ruler. It's going to be more precise. And I will draw the hypotenuse here, because this is a right angle triangle. There we go. So that would be 3 times the measurement of the original triangle. All right, B, we have 150%. Ooh. Okay, so let's see. Oops. Let me see if I can find a circle. Yeah, I do. Okay. So right now the radius is, what is it, 2? So let me just adjust it. So we're starting here. Nope, it's not working right now. There we go. We're starting in the center, going out. That's 2. So that is our 100%. We're going to 150. If you're not sure how that works, you can divide this by 100. That'll be 1.5, and that'll give you the scale factor. So really, what I have to do is I'm going to multiply my 2 times 1.5, which is going to give me 3 squares as a radius. So we're magnifying again. And let's see if this is going to work. Nope, this is not working right now. I think this circle can draw it. Oh, there we go. So let's say that's the circle. I'm just going to adjust it. There we go. That's kind of it. So now the new radius is 3 squares instead of original 2, and that is 150%. The next one, so these were both enlargements, by the way. The next one, as you will see, we have a rectangle. It says a scale factor of 0.25. So that means if I look at these sides, so we have 1, 2, 3, 4, 5, 6, 7, 8 squares. So all I have to do is take my side times 0.25 and then do the same thing, 1, 2, 3, 4 times 0.25. So that'll give me the length and width, and it's 25% really. So for the length, there we go. Yeah, that's actually okay. So for the length, I will have only 2 squares. There we go. And for the width, I'm only going to have one. Now that I'm thinking about it, I think I might have used the other option easier. Yep, this is not the greatest rectangle. I'm going to try and use the same tool that I used for the circle. Let's see if this works. Alright, that's kind of that. Yes, that is a little bit easier. There we go. And that's my um, shape B. So this was 2 and this was 1. So obviously there's a reduction. And then we're going to D. It says scale factor of 50%. 50% means that it's half the size. If you look at it, we have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. This is a square. Half will be, um, let's see if this, oh yeah, I can do the square. So that means it's going to be 3 by 3. Yes, there we go, perfect. There we go, 3 by 3. Half the length, half the width. So that is our reduction as well. All right, moving on to next question. For each new diagram you drew in question 3, state whether it is an enlargement or reduction. So again, I'm going to put E, and I'm going to put R here for reduction. So if we go back, we will see that in the first two, A and B, we had an enlargement. So we went from a small triangle to a big one, from small circle to a bigger one, and then we have a reduction for C and D. We went from a bigger rectangle to a smaller one, and bigger square to a smaller square. So we have E, E enlargement, and R for reduction. There we go. That was easy. So question number 5. On an architect's blueprint of a building, 1 centimeter represents 2 meters. So 1 centimeter to 2 meters. What scale factor should the architect use to determine the actual distances or lengths? So what they mean by that in this case is we have two different units. So how are they going to calculate this? So if we want to convert this to the same units, we would have 1 centimeters to 2 meters, which if you remember, 1 meter is 100 centimeters. So 2 will be 200 centimeters. So all he has to do is a scale factor of 200 to calculate what the distances, lengths, all that stuff is going to be. So he would take the original. No, he would actually take the. Let me see. 1 centimeter represents blueprint. Okay, so he would take the blueprint of 1 centimeter, multiply by 200, and that would give you the amount of centimeters. And then from there, you can use the conversion to find how many meters. You could also use a scale factor of 2, but with understanding that you're converting from centimeters to meters, so automatically you would get meters in your calculation. All right, moving on to number 6 says the scale factor used to create the scale drawing of a computer chip was 300%. Determine the actual length and width of the chip. So 300% means that this is an enlargement. So this chip here that we're looking on the side, it's not going to be that size. It's going to be way smaller. So 300%, we would actually have to know right now how big this chip is here. So I loaded up a ruler. There we go. Oops. There we go. Now my measurements are going to be a little different than yours. If you're using your ruler, it might measure something else. Let's see, so if I'm putting the ruler here, it's hard to see there. It looks like 5.3. So the 5 point, oops, undo that. It looks like it's 5.3 centimeters. The original, so this is the diagram size now. So 5.3, and we're going to look at it as 300% is our enlargement in this case. So if you kind of remember that 300% really is a scale factor of 3. So that means if we have something that's enlarged to 5.3 and we wanted to find out the original, the actual length of the real chip, we just have to go backwards. So in this case, so we're just going to divide 5.3 by 3, and that's going to give us one of these sides. So let me just grab my calculator. It says 1.77 centimeters. So that will be the real size of the chip. I didn't actually check, but it is possible that it looks like a square, but I will, let's see if I can do this. Yep, I'm going to try and measure this side here. Yeah, it looks like it's a square, so I don't have to do anything else. So it seems like the original chip is 1.77 centimeters by 1.7 centimeters. And that's it. Moving on to number 7, says draw this sign using a scale factor of 40%. So I know it's going to be smaller. Um, I will have to measure this radius. Let's see. It's not going to be the most exact thing, but let's see. Radius, it looks like it's 6, which is great. So that means that my original radius, here we go, radius is 6 centimeters. Again, if you're using your ruler, it might be a different measurement. I'm just going to use the one I have here. And it's 40, it's going to be 40% of the original, so that means I'm going to multiply by 0.4, and we will know what that is. That is a 2.4 centimeters is going to be the radius. I'll put it as radius B. So if see how I'm going to do that here. I have a circle, and let's see if this is going to work. 2.4. Oops. That didn't work out. Let me just undo that. Go back to the circle. So radius of 2.4. There we go. So I can go all the way to 2.4. That seems to be it. And then I can move my circle. There we go. And I can use a little bit of ruler, a straight line. Yes, I can. There we go, something like this. Oops, not that much. There we go. And then what we can do is we can, here we go, we can measure how long it is from here. Okay, let me adjust it from here to here, and we can make the appropriate adjustment and then do the same thing with these. But I'm not going to spend too much time. The main thing is this part here, this calculation, how we got to the smaller size. All right, moving on. Actually, I just realized I made a mistake. Yes, I did. Because I'm looking at this circle, this smaller circle here. That doesn't seem like 40%. It seems too large. So here's where my mistake is. I'm going backwards, going backwards, going backwards, erasing the circle. Originally, when I calculated, not calculated, when I measured this part here, that's not the radius. That is the diameter. Let's see, so we'll erase this, we'll erase this. So this is diameter, not the radius. Diameter, not the radius. If I wanted to find the radius, I need, there we go. The radius of B is going to be half of 2.4, which is 1.2 centimeters. So now I will go and do this the right way. And hopefully that'll look a little better. Here we go. 1.2 There we go. That looks much better. That looks like 40% or smaller, right? And then I can adjust everything else, same measurement. Like I said, same process. I could go and measure this part here, from here to here, do the 40%, and so on and so on. All right, moving on to number 8. It says draw this logo using a scale factor of 2. So again, it seems like these last few questions are more hands-on application. So here we have it's a square. It's around 1.2. Oop, let me just try and do it. Yeah, around 1.2 centimeters. Seems like 1.2 by 1.2. So if I have a scale factor of 2, that's multiplied, which means that it's going to be 2.4. And I think I will use that square. There we go. 2.4 is going to be right there. And now, let's see. Oops. I want to see if I can tilt this. Yes, I can. And maybe just a little adjustment. And see if we can draw a diagonal. There we go. And I can shade this in and all that stuff. The most important thing, again, factor of 2, which means double the size in this case. And my little representation shape is 2 times the factor. All right. Moving on to next page, we have a space shuttle. So the scale factor using to create these scale drawings of a space shuttle is 1 to 475. So that means on this picture, 1 unit, whatever it is, 1 centimeter or 1 inch is 475 centimeters or inches in real life. It says measure the length and width of the drawing. Use these measurements to determine the length and width of actual space shuttle in nearest to the nearest meter. So I'm going to need my ruler again. Let me just get another one. Here we go. I have a length. So based on my ruler, the length is 9.2, it seems, centimeters. And width is, let's adjust that again. It looks like 5.9. 5.9 centimeters. So if I wanted to find the actual one, I guess I can set up, I'll do one with the proportion and I'll do the other one the easy way. So the first one, I know that the diagram here is 1 centimeter to 475 centimeters in real life. And then my diagram measurement is 9.2 centimeters, and we're trying to find what it is in real life. So this is where cross multiplication is going to work well. So x times 1 is just x, and then 475 times 9.2 is 4,370 centimeters. And if I divide this by 100, just to get more realistic image of what this is actually 43.7 meters. That's pretty large. If we wanted to do it the easy way, which I will do with the width, all I have to do is multiply 5.9 by 475, sorry, and I will get what my width is. So I'll put W for width. So 5.9 times 475 is 2,802.5. This is centimeters. And if I wanted to see how many meters that is, divided by 100, which is just 28 point, I'll just put all of it, 0.25 meters. Still pretty wide. So that is Space Shuttle. Moving on to the next question, we have some kind of a windmill. Yeah, wind turbine. It says this scale drawing of a wind turbine has been done for a magazine article. The actual turbine has the hub height, which is, as you can see from here to the ground, is the hub height is 80 meters. So it says 80 meters. What is the diameter of the actual rotor? Okay, so this is kind of a multi-step question. First, we want to see what kind of scale factor do we have here. So again, I will get a ruler. I need a ruler. There we go. I have to find a scale factor, and what I'm going to do is I'm going to use the actual height compared to the diagram height for this uh, hub height. Okay, there we go. I'm going to just round it to 6, so 6 centimeters to 80 meters. If you want to put it into the same units, 6 centimeters to 8,000 meters, centimeters, sorry. And then to get our really scale factor, I'm going to divide everything by 6, just to get divided by 6, divided by 6. So 1 centimeter, I don't know why I'm writing 16, 1 centimeter is equal to 8,000, 8,000 divided by 6. Here we go. 133.3 and so on and so on centimeters. So that means that is my scale factor. So I'm going to use this for my diameter. So my diameter, I'm just going to use here we go. My diameter is, it looks like it's 3 centimeters. So my diameter in my drawing, diameter from the drawing is 3 centimeters, and I will use the scale factor of 1,333.3, which means I'm just going to multiply that by 1,333.3, and I'm going to get the diameter in actual rotor. I'll put AR, and times 3, and it is 4,000 centimeters. And if you're not sure how many meters, we'll divide this by 100, which is 40 meters. So that's pretty large. It seems like diameter is half of that hub height. So that's fairly large. And that's how you're going to have to do this. It's kind of a multi-step question. You have to get some information from the first part that's given to you, and then find the missing, what they're actually looking for. All right, the next one says, what scale factor was used to create the diagram? Well, this is my scale factor. So we actually found B by kind of approaching this question at the beginning. So, I mean, we solved B as a part of A. So that is the scale factor of 1 centimeter to 1,333 centimeters, or I guess I could also express it in meters. So I guess I could say it's 1 centimeter to 13.3 meters, or 1 centimeter to 1,333. All right, that's it. So the two questions that you have at the end, 11 and 12, you can try that on your own. And we are done with this chapter. And if you have any questions, please email me, and I will assign some additional work for this week. Thank you. Bye.